Sudoku, a classic problem for programmers to try and solve. Today, we're going to do the same, but we are not really going to use, a proper efficient algorithm to do it. We're just going to attempt to brute force it using recursion. The purpose of today's video is to sort of demonstrate recursion in an applied context. I know most of us aren't very comfortable with recursion. So yeah, hopefully today's application will help dispel a little bit of that feeling. Without further ado, let's jump right into our Random Wednesday episode. Hello and welcome back to another Random Wednesday episode. Now, in case you're not familiar with the rules of this classic brain teaser, here's how it works. You have a grid of 9x9 squares further divided into 3x3. The idea is we want to fill up every square with a number, and this number must be unique within its square, its row, and its column. Usually puzzles start with some numbers pre-filled in, and what you can do is just logically, you can induce the rest of the numbers. With just that one rule, you can basically fill in every single square. Of course, that is if the puzzle was constructed properly, which, well, if you do see puzzles, say on newspapers or in books out there, yes, those are made properly, they have exactly one unique solution. So here's how today's video is gonna work. Essentially, we have it split into 3 parts. At the beginning, I will briefly describe the architecture of our entire system, right? How data is gonna flow from one point to another. In our second part, we will sort of build, the basic underlying stuff. And then finally, at the very end, we will actually jump in to build our recursive algorithm. I will provide timestamps in case you, want to skip past the boring talk and go straight to the recursion. So yeah, if you want that, do pop open the video description. You'll also find a link to the completed project files, in the video description. So let's jump into the first part, which is our architecture. Now, for the purposes of this program, we will be using the Python programming language. The board itself will be represented as an array of strings, where dots basically represent empty squares. So yeah, essentially we pre-populate our board, right? And the program will take over. Our program will actually employ 2 separate strategies to solve this problem. First, we will start off with the so-called obvious solution. And what that means is we are going to look at a square, and if its surrounding squares actually precludes all numbers except 1, we will pick that number. This is basically the most basic way to solve it according to the actual rule. And we do this so we don't have to do quite as much recursion. So yeah, that's the idea. We're going to actually run through the grid from top left to bottom right and fill in as many obvious squares as we can. We're going to then loop our way up and basically keep doing that until we end up in a stage where there are no more obvious squares. And that is where the recursion starts to kick in. So very briefly, here is pseudocode on how we can actually solve this problem. Let's look at it bit by bit. First, of course, we want to run the fill obvious cells function. And in fact, if we're lucky, if the puzzle is simple, the puzzle could be solved right away using that. And as a result, we simply return true. We don't have to do any further computation. Of course, it is entirely possible for us to encounter a contradiction. Generally, this will only happen after we perform some recursive call, after we have made some guess. If we encounter a contradiction, we return false, because we don't want to do any more work, right? Something is definitely already wrong. Of course, these are not the only 2 conditions we can encounter. It is entirely possible that, well, neither of these things are true, and what that means is our next step is a guessing step. So, we need to find an empty cell and basically get all the possible values that can occur at that cell. Then we simply loop through the possibilities and basically fill in the first one at a cell and run solve to see what happens. So that will be a recursive call, right, to this same function. Don't forget that it can return either true or false. So what this means is if we get true as a result of this recursive run, we know that we are done. We've managed to actually get a correct guess and solve the puzzle. If we get false, that means that our guess must have been wrong, and as a result, we want to undo all the changes that have been made. Once that is done, well, since we haven't actually left this loop, we're going to go back up, we're going to pick the next possibility, and we're going to make our recursive call again. This loop can happen as many times as we need. Basically, at the very end, we will have visited every single possibility. Of course, if one of them eventually leads us to the right answer, that would stop the loop. Of course, we have to prepare for the case in which none of the possibilities here are correct, and that would happen if an earlier guess was wrong, and this basically leads us to contradictions all the way down. If that is indeed what has happened, we will find ourselves basically falling out of this loop, which is why we write a return false statement over here, so that we can basically report back to our caller that something was wrong along the way. So yeah, that's basically our entire algorithm, and the power of this algorithm is that one guess will basically call a function that is capable of making a subsequent guess. In fact, this goes on, and basically at any point of time when we encounter a contradiction, we basically only go back to undo our latest guess, and from there we can make a subsequent guess. This can go as deep as required. Sometimes it's possible that all of these guesses lead to contradictions, so we backtrack even further and change a prior guess. Eventually, we'll end up at a stage in which everything is completed. And yeah, we've basically solved our puzzle that way. You'll find that this algorithm is actually pretty quick. It can even solve an empty board in basically no time at all. So yeah, that's how we're gonna approach it. You've just seen the pseudocode. Now let's go in and write actual Python code. So alright, let us build our Sudoku solver. Now, what I have here is the board already there, right? As mentioned, we're just gonna have it as a list of strings. Now, we're gonna be quite nice about, following our top-down programming kind of style. So we're gonna have everything split into functions. I'm gonna start with a main function, right? And we're just gonna call it at the end. To immediately contradict what I just said, we're also gonna be using global variables, and that's just for the board, right? So we're gonna do it this way so that, well, every function can actually touch the board. Now, there is one special thing about strings in Python, and that is the fact that they are immutable. You cannot actually change the contents of a string. So what I'm going to do is, I'm actually going to, well, change up every single line of text into a list. In fact, I'm going to go ahead and use an enumerate function here. And what this does is, it basically gives us back the index of the current line, as well as the content itself. Right, in fact, I'm going to very quickly just run this and you will see this in action. Basically, what this gives us is, well, the index, right, you can see the 0 here, and then the contents of that particular line, which is right here. So basically what we're going to do is we're going to use this to replace the lines on the board. So from the board, we're going to grab, that particular line, and we're going to change it to the line converted to a list. The result of this operation is it's going to convert every character into an actual array item. So if I were to just print this out here to show it to you, well, we now have lists, right? Everything in a format we can actually modify. Now, again, this one is, just a little bit of extra Python, right? So don't worry too much about it. The idea is, well, we want to convert a list of strings into a list of lists that we can, well, edit. So alright, once we have this, basically all we're going to do is we're going to call a solve function. The main bulk of the work is going to happen here. And we're going to actually write that separately. So let's go ahead and do that. Later on, we'll be doing our recursion here as well. Alright, so here's how we're going to approach this. Essentially, of course, we want to be able to access the board itself, right? And then we're going to go through every square. Of course, in order to do this, we will need our doubly nested for loops. So here's one, and here is the other. So basically what this gives us is, well, different values of I and j, and what we can do is we can actually use that to check each cell. Now, here's the deal. We're going to write a function called getPossibilities, and basically this function will check a particular cell, of course referenced by its so-called coordinates, and then it's going to return the items back. So this could be a list, right? The idea is, well, this list tells us what are all the numbers that are possible in that particular square. if only one item comes back. What this means is that square must have that particular value, right? It can't be anything else. And therefore, we're going to actually update that particular square so that it takes on that value. So that's the idea, right? If only one item comes back, we update it to that only value. For now, let's leave it at that, even though you'll find that later on we need to change some other things. Let's now go ahead and build our getPossibilities function. Right, of course, it takes in two parameters. We need it to touch the board. And first and foremost, right, before we do any work, let's check to see if that particular square has already been filled in. So if it's not a dot, then let's say we return false. So then we're going to have to add another line here. If possibilities equals to false, right, that means we already, well, know the value. That means, it's not an empty square. We simply skip past this particular iteration. So in case you're not aware, right, continue means just don't do any of the other stuff, right? We'll just go to the next iteration. If we end up here where our cursor is, we have to find out what possibilities there are. So now we're going to build our possibilities object. And basically what we're going to do is we're going to use a set, and we're going to start with everything first. That is all numbers from 1 to 9. As we find contradictions, right, if we find that one of them is not possible, we will just get rid of it. Now, there is a not so often used Python feature, in fact, two of them that I'm going to use here. Firstly, that is the concept of a set. And secondly, is the concept of comprehension. I'm going to go ahead and write this statement first, right? And then we'll see how it works. Basically, we're going to write it like this. And in range 1 to 10. So let's try to understand what's happening in this statement. I'm going to actually open up a Python console window and we'll see. Okay, so the first thing we said is range from 1 to 10. Now, to visualize this as a list, you will see that it basically gives us the numbers 1 through to 9, right? Which is exactly what we want. This lists all the possible values you're going to get back. Now, what we realize is that these are numbers, but what you have in your board are actually strings. So we don't want to use this for comparison purposes. We want to convert everything to a string. Unfortunately, we can't just do something like this, right? We can't just convert the whole thing to a string. To do this, we use a special Python feature called comprehension. What you're doing is you're basically using a for loop syntax to build something like a list or a set. For example, here are just, our square brackets to build a list. And what I can say is for I in range 0 to 10. In fact, let's use, just the same things we have used earlier. Now, this gives you the same result, right? The exact same result as saying list, range from 1 to 10. However, what we can do is we can do a further processing step over here, and that is to convert our I to strings, right? So now you have strings. You can use this method to, easily write something like I times 2, for example, right? And now you get everything that is double. So yeah, this is just convenient Python syntax. So okay, we have our strings, and in fact, we're going to change this up to use curly brackets at the end. Now, what we have created here is what is known as a set. The first thing you'll notice is that the numbers are all jumbled up, right? In fact, if I run this a couple of times, looks like I get the same values. If you do that in several different editors, you may get different values. But the idea is a set is unordered, just like a set in math. What's even more important is I can now do set operations. For example, I can take away, say, 8 and 1, right? So I'm just constructing another set here and performing a subtraction. What you find is that I do end up with, just those values missing. If I try to subtract it with something that doesn't exist, right, it's fine. It doesn't complete. We just end up with, our actual original set. Similarly, if you try to take away something and then you try to take it away again, no problem, right? You just get back the same result. Nothing happens. So this allows us to write things in a very convenient manner. So to find the list of possibilities, we just need to implement a few more loops. First, let's try to check our row. Now, a row is the easiest to do because, well, we just need to say for value in. And what we're going to do is we're going to go to the board, but we're not just going to iterate through the board, right? This is going to give us a bunch of arrays back. Instead, we just select the particular row we want. In this case, it's specified to us by I, right? So it's going to just go to a particular row, and it's just going to give us the contents within that row itself. So yeah, very convenient. Basically, now I just take our possibilities set and subtract away each value that we've seen. Now, what this means is, for example, if we are looping through this line, well, at first, we'll try to subtract away a dot. There was no dot in the set in the first place, so nothing's going to happen. And we're going to just repeat this, right, a whole bunch of times, and it's going to be just fine. Finally, we see a 4. And if we were to actually take that away, you will get basically 1 through 9, but without 4. So yeah, for a complex line like this, right, basically all these values will get eliminated. So yeah, that's the idea, right? A subtraction can take no effect at all, or it can basically remove one possibility from our set. So this is for a row. Let's now do it for a column. It's slightly harder to do it for a column, right? We're going to have to actually, well, properly loop through it. Basically now, right, it's exactly the same. We just have to access it in a slightly different manner. Now basically, our index is feeding our first parameter, but our second parameter is fixed. What this means is for one particular j, in other words, for one particular column, right, what we're going to do is we're going to just go from top to bottom and do the same thing. We're going to just take away stuff that we encounter. So now what we've done is we've taken away possibilities in a row and a column. Now we just have to, well, find our particular square and do the same. Now, the algorithm to do this is fairly interesting. You see, what I want to do is I want to find sort of which square I belong to, right, which little 3x3 square, and from there, well, get all the values inside. Luckily, which square I am in can be found with a simple division. Basically, where I start in terms of the rows is just my current position divided by 3. I use double slashes here because that means an integer division. So if you're looking at one of these 3 rows, right, their positions are going to be 0, 1, and 2. If you divide that by 3, without a remainder, you will always get 0. These 3 will always give you 1. These 3 will always give you 2. So yeah, that's the logic, right? And we apply the exact same one to our j, right? In other words, our columns. Of course, these numbers are not so useful. If we multiply them by 3, they now represent an actual position within the list itself. In fact, as its name implies, these are the starting points to basically, well, start to look for values. Essentially, we can now slice out the relevant rows. And how we do that is by taking the board and saying we only want rows starting from I start and ending at I start plus 3. So for example, now if I'm on row number 4 over here, the division will give us 1. Since we multiply that by 3, we will end up at 3. Row number 3 is this one right here. If I slice from row number 3 all the way down to that plus 3, I'm essentially slicing rows 3, 4, and 5, like so. So this will give me back all the relevant rows. I basically now need to find the columns as well. So in fact, let's name this something different. Let's call it a subboard. So we're going to be making use of enumeration again, right? And essentially, we want to look at our rows within the subboard. Basically, we want to perform slicing. Right, that's why we do enumeration, because we actually want to replace the individual rows. How do we want to replace it? In fact, let me call this row here to make this clearer. We're going to take each row and we're going to slice it further to give us just the columns we want. So what we've created here now is an actual slice for the square we are interested in. Of course, that has just basically isolated out the actual square. We still need to loop through the contents. So how we're going to do this is we're going to say for row in our subboard, right, there's only going to be 3 of them. We're going to loop through the columns as well, right, again, there's going to be 3 of them. Essentially, we're going to do the same. Possibilities, subtract away the current item that we're looking at. So what we've done is we've taken our possibilities object, right, we've given it everything from 1 to 9, and we've basically gone through a process of cutting away everything that is precluded by the row, everything that's precluded by the column, and everything that's precluded by its own square. So what we get back eventually, right, is, well, whatever possibilities there are in that particular square. For our convenience, we're going to basically cast it back into a list. So yeah, right, that is how we do it. Now, before we go further, let us test this. I'm going to do that in our main function. And basically, I'm going to check a particular square. Let's check a square on this row and this column, right? Just because there seems to be a lot of things here. Now, this square cannot be 1, 2, 3, or 4, right? Because of these 4 guys over here. Well, it also cannot be 9. Oh, and it cannot be 5 as well, right? Because 5 belongs in its same square. So the results we expect to see back are 6, 7, and 8. And that's it. So the position of this square is 2, 2, right? Let's go ahead and say print getPossibilities at 2, 2. Fingers crossed there are no bugs. Let's run this. Right, there we go. We have 6, 7, and 8. Of course, in a jumbled up order because we used a set as an underlying data structure. Of course, we've converted it back to a list at this point, but it's not going to give us the right order back because we didn't tell it to sort, right, the contents. Alright, awesome. We now have our getPossibilities function all set up. What we have here now is a solve function that is able to just apply the rule and fix up as many cells as it possibly can. Now, the thing is, our solve function only does one pass, right? It goes from top left to bottom right and it finishes up. Basically, we want this to keep going until it's no longer able to make any further changes. So what I'm going to do is I'm going to insert a new variable here, right? Something changed, and we're going to say false first. And every time it's actually made a change, right, that will become set to true. So we're going to use a while loop here, right? And I'm just going to cheat and use a, forever true loop. And it's going to do this once, and it's going to check. If something changed equals to false, right? Oops. Wait, hang on. Let me just fix the capitalization here. Right, okay. So if nothing has changed within an entire pass, what this tells us is that, well, we are basically done here, right? We cannot actually do any more. Of course, at the beginning of each iteration, we should set that value to false. So yeah, in fact, I don't need this here. Basically, the idea is this loop will keep running until it's not able to change anything else. So we're going to do solve, and what we're going to do at the end is we're going to just see the state of the board. Alright, so off screen, I've actually made some changes. There are a few places in which my trues and falses are, not the right case. So yeah, because, well, I do a lot of JavaScript and it's completely okay to do that in JavaScript, but not here. So I've changed everything so that it is uppercase. Another thing I've changed is I have actually picked a much easier board to start off with because, of course, this particular technique is kinda, well, on the simple side. So now let's try and run this. And in fact, it solved the puzzle for us, right? I don't see any dots anywhere. Now, let's just try and print this out in a nicer manner. So let's go ahead and build a printBoard function just for fun. Right, so I'm going to do it at the end here. Def printBoard. Again, it's going to globally access the board itself. We're just going to do a simple loop through here. Row in board, for column in row. Right, and basically what I'm going to do is I'm going to print out the value at the column. Right, we don't go to a new line. But at the end, when we're done, we create a new line. Right, something like that. Very, very simple. So now I can just say printBoard like this. Oops, no zero. Right, there you go. This is actually the full solution of this puzzle. Because this is an easy type puzzle, right, it's actually able to fill everything in. Right, by just using the rule, we have the answer for everything. So in fact, up until this point, what you have is able to solve, well, the more trivial puzzles. Of course, I've had to do this because, well, with the original board I had earlier here, I found that, no matter what I did, well, it's not gonna fill in very much. In fact, it doesn't look like anything has been filled in at all, right? So this is because, well, this is a difficult board, right? It's designed to be harder, more confusing. And what that means is there is no straightforward solution, unlike the other board. So yeah, both of these were generated by a program called Sudoku. I will put a link to it in the video description if you are so interested. But yeah, basically, well, what we have is enough to solve one board and completely useless against another. This is where our recursion will come into play. Alright, now for the fun part. Now that we can solve things using the rule, we can now move on to our recursive guessing. Our existing solve function is basically sort of the trivial version, right? So what I'm going to do is I'm going to just move it, in fact, to a new function signature like this, which I'm going to very unglamorously call fill all obvious. Right, so this is going to be basically what we're going to be doing here. And basically, how we're going to call our solve function is we're going to call fill all obvious first. Now, we're going to need a way to decide whether or not we need to guess, and that's going to basically involve finding out whether the board has been filled or not. To do this, we're going to write an additional function which checks to see if, the game has actually been complete. This is not going to check for correctness, it's just going to check to see if there are empty squares on the board. So I'm going to say def is complete. Right, and I'm going to, loop through everything here. For row, for column, in row. Basically, if we ever see any column, right, that has a dot, we can return false, because that means, it's not complete. If we end up here after going through our entire loop, what that means is we haven't encountered any, square that has a dot in it, so we can return true, right? This is going to tell us that, our game is actually complete. So what we can say now is that if is complete, return true, right? That means our job here is done. Otherwise, we're going to have to actually do our recursive stuff down here. Now, what I'm going to do is I'm going to actually look for a particular square, right? So I'm going to just sort of scan through my list to find an empty square. I'm going to get possibilities on that square and start to guess using the possibilities we have. So let's begin. I'm going to say for row in board, right? So what this means is we do have to do a global board over here so we can touch the board. For column and row, if column is a dot, I'm going to actually collect the row and column index and basically stop looping. Of course, in order to do that, I'm going to actually have to do an enumeration. Right, same deal for the column. And what I'm going to do is I'm going to collect the values in separate variables. Right, something like this. ij is the row index and the column index. So what that means is, what I get here in my I and j are the values of the first square that is empty. So what I'm going to do is I'm going to just get my possibilities from that particular square. Essentially then, I'm going to loop through that particular list and I'm basically going to just try it. I'm going to set the board I and j to our first value, right? And then I'm going to actually, attempt to iteratively solve. Of course, I will have to do some if statements, right? So basically the idea is if, it ends up actually being solved, then we are good. So solve will return us a result, right? If it's actually set to true, then we can go ahead and return true, we're done. Otherwise, we're going to actually have to retract our answer. Now, here's the deal. The retracting here is very important because not only do we have to change the value at this particular position, but we have to undo the results of anything we have done in this particular step. Because what happens here is that, assuming that this value is correct, we've gone ahead to populate more squares. However, we've realized that that assumption is wrong, so we have to come back. The easiest way to do this is to actually copy out the board. Now, for this, I'm going to be using a library called copy. And what this does is it allows us to do what is known as a deep copy. So what I'm going to do is I'm going to take a snapshot of the particular board at this point in time, right? And basically, if I realize that, well, something has gone wrong along the way, I want to roll back to what I've gotten in the snapshot. Basically, a deep copy is going to just delve deep, right? And it's going to copy everything out. So that is how we basically take our snapshot and we store it later on if needed. Now, we just need to implement one more very big thing and we're done. And that is when our fill all obvious, actually chugs along and it finds that, well, something is actually wrong, we want to be able to convey that information. Here's the deal. If something is wrong, our possibilities list will have a length of 0, right? So that is a problem. If we end up with a cell that, nothing fits in it, we know something is wrong. I'm actually going to handle this by raising an exception. Last Friday on Friday Minis, we actually talked about exceptions, but that was about handling them. Over here, we're going to actually create them as well, using a function called raise. Basically, we want to say, well, raise a runtime error. And, well, we're going to say that there are no moves left. This will cause this function to immediately terminate at this point. Now, we're going to go back to our solve function now, right? And the only point of time in which we have a chance of seeing this happen is when we call fill all obvious over here. So we're going to actually surround this in our try block, right? Like we've seen last time. And accept, right? So that we know, when something wrong happens. When an exception crops up, all we're going to do is return false. What this tells us is that this will plug into, well, our previous function call over here, right? So if our result ends up false, we know something is wrong. So yeah, in fact, we are basically done. We also have to get our, well, whole thing to return at the end here. That is, if we go through all our possibilities and none of them have worked, what this tells us is that something was wrong earlier on as well. So we return false. Well, that looks like we're done, right? In fact, we are. So let's go ahead and run our code here, fingers crossed. There you go. We just have our whole board filled in here, right? So this is the more complex version of the puzzle. And yeah, it seems to have found everything. Now, just for fun, what I'm going to do is I'm going to just populate this with an empty board. And the interesting thing is when we run this, we do actually get a result. I'm going to leave this open and I'm going to run this again. Notice that we get a completely different result this time. That's right, we give it an empty board, it's able to solve it, right? This is, well, correct according to Sudoku rules. And yet, we have two different results. This is in fact a side effect that comes about, right, because we have used sets. Don't forget that sets are unordered, and as a result, well, we can get inconsistent results from time to time. In fact, yeah, you'll realize that if I run this 10 times, I will get 10 different answers. And that is, I guess, sort of the beauty of the solution. Anyway, well, we're done. This has been our Sudoku solver. And yeah, this code will be available for you to look at in the video description. But yeah, that's basically it in barely, well, 137 lines, right? We have a fully fledged, brute force, recursive Sudoku solver. And there you have it. That is basically it for our little Sudoku solver. Try it yourself. You can basically put in any puzzle, right, and it will find a solution. If the puzzle has multiple solutions, it will find a random one. As mentioned, sets are technically unordered, and because we've used sets, well, basically we can end up getting any possible result back. So yeah, there you go. If you want to take a look at the code itself, do pop open the video description, right? There will be a download link. If not, well, we're done. That's all there is for this particular episode. I hope it's been a fun experience for you. It's certainly been, quite a sense of achievement when you can actually get something like this working. Like I said, this isn't the proper way. There are actually algorithms that can rigorously solve Sudoku without guessing, but that would be, another level of complexity, which we're not going to. That's all there is for this particular episode. Thank you very much for watching, and until next time, you're watching 0612 TV with NERDfirst.net. Thank you very much for watching. If you like my work and are feeling generous, you can shoot me a one-time donation on PayPal or sign up for a recurring one on Patreon. Of course, you can simply like, comment, and subscribe. You know the deal. For more videos, links to my channel and a related playlist are on screen. Thank you for your support.